It's my pleasure to welcome everyone to the Oxford-Bristol Set Theory Seminar. And the speaker today is Gabriel Goldberg from Harvard University. And he's going to be speaking on even ordinals and the Kunen inconsistency. So go ahead, Gabe.
Okay, so I've been told to try to share my screen in presentation mode. And if anyone was at the CUNY Set Theory Seminar, they probably saw me be unable to do that. So I'm going to try again, and hopefully it won't take.
Just enter full screen there is what you want, I think.
Yeah, but then, okay, this is great. Now I can see you guys. For some reason, it wasn't working. Okay, I think this is fine. Okay, so my talk is about large cardinals beyond the axiom of choice. But the last talk I gave was about why I don't think these axioms are consistent. And this talk is about why I think these axioms are consistent. So one of the two talks is right, and hopefully maybe there's a middle ground and they're both right, but at least one is right. Okay, so I'm going to start by talking a little bit about the consistency of large cardinal axioms. And I don't know, this section, I'll pretend that it's going to be generally accessible, and then I'll talk about the Kunen inconsistency, and it will be less accessible. And then I'm going to talk about large cardinals beyond choice, and some new results about choiceless rank-into-rank axioms. And at this point, it'll only make sense to you if you've seen some of this stuff before, probably. Okay, so the new material is like a new result about periodicity phenomena that arise in the hierarchy of choiceless large cardinal axioms. This kind of periodicity phenomenon, I don't know, it's sort of new. It doesn't occur anywhere else in set theory, except maybe in the theory of determinacy. So there are some analogies with determinacy that I'll talk about. And then I'm going to talk about ultrafilters in the context of choiceless cardinals. And I'm going to speculate again about whether they're consistent. Okay. So here's the falsely accessible part. So large cardinals, what are large cardinals? They're principles that assert, the existence of large transfinite cardinals, so cardinals that are so large that you can't prove that they exist in the standard axioms of set theory. And that's a good thing about the axioms, because it means that they go beyond the standard axioms. And you'll see some examples of extremely strong large cardinal axioms in this talk. Okay, but the point of large cardinals, or one of the points, is that you can reduce the consistency of arbitrarily strong theories to the consistency of large cardinals. And that means, if you want to prove that a theory is consistent, usually what's done for strong theories is you start with a large cardinal axiom and you use it to build a model of the theory, typically by forcing. And you can also gauge the strength of a principle or a theory by trying to figure out what large cardinals the principle proves to be consistent. And usually you can sort of get an exact matching and figure out the large cardinal you need to build a model of the theory, and exactly which large cardinals the theory can build. And, that's sort of the idea of inner model theory. Okay. So the question arises, the sort of important question is whether large cardinals themselves are consistent. And this, consistency of all the theories that are studied in set theory sort of reduces to this question. So you can't really prove it in any meaningful sense because of the Gödel incompleteness theorem, which says if you have some theory, you can't use that theory to prove its own consistency. And so you're not going to get a meaningful proof of the consistency of any principle pretty much, because you'd have to start with assumptions that are already stronger than the principle you're trying to prove consistent, which just doesn't seem very useful. Okay, but there is some evidence, which is not the same as a mathematical proof, that many of the large cardinal axioms currently studied are consistent. I mean, the consistency of small large cardinal axioms is, as certain as many empirically established facts, I think. Okay, the sort of main reason people think large cardinals are consistent, or one of them, is often called structure theory, although I've never really gotten what structure theory means. But okay, here are the examples of structure theory. I don't know if the term structure theory is used outside of maybe the philosophy of math, and I couldn't really find. I didn't look this time, but when I was an undergraduate, I looked for a definition of structure theory because it seemed like such a vague term, and I didn't find it. Okay, so one sort of structure theory is the theory of determinacy, which is sort of part of descriptive set theory, the theory of basically infinite game theory. And it turns out that this is, deeply connected to the existence of fairly large cardinals. And there's like an incredible amount of theory that's been developed for determinacy, and a theory that's been developed to prove determinacy from large cardinals and to extract the consistency of large cardinals from determinacy principles. And there's sort of so much that's known, and everything seems to be answerable in the situation, and the answers all seem very nice, and it would be sort of unprecedented in all history of human thought if the whole thing just collapsed. But it would be exciting. Okay, but so that's the sort of justification or evidence that is given by structure theory for consistency of large cardinals. And there's similar stuff for even larger cardinals. There's lots of work that's been done on forcing from large cardinals, and maybe it's sort of weaker evidence of the consistency of very large cardinals. Oh God. Can you see that I'm receiving text messages on my computer? No, great. Okay, so another really important kind of structure theory is the intermodal theory of large cardinals. So this is a theory in which you build models that satisfy large cardinals, but all of the properties of these models can be determined in CFC. So you build very specific models of large cardinals. And that's sort of nice because if you have a principle, sure, maybe you can believe that it's consistent, so there is some model, but it is nice to be able to point to a specific model, I guess. So for example, for very pretty small cardinals, the inner model L satisfies these large cardinal axioms if you want, and the inner model L seems like a very specific and concrete mathematical structure. It's not so different from a structure like the natural numbers. It doesn't seem ambiguous in the way like the Platonic set theoretic universe seems ambiguous. Okay. Okay, so then the other reason you might think large cardinals are consistent is that they're true. And I put a question mark there to distance myself from it. So what does that even mean? Like large cardinals really exist in some Platonic sense. So there really is an inaccessible cardinal and a super compact cardinal or whatever. And that's why they're consistent. And I mean, it sounds naive sort of if you say it that way, but I mean, why do people think that piano arithmetic is consistent? I mean, it's because they think that the structure N really exists. I mean, most people who think PA is consistent think that. And similarly, I mean, you could also think, large cardinals really exist inside their inner models. So L is real or something that, I don't know. The structure theory sort of argues that, it would be ridiculous if large cardinals weren't consistent because this whole theory would be vacuous, and that has never happened. But it doesn't really say why the principles are consistent. It just sort of says we have a theory and it's probably consistent because why else is it there? But yeah, there's no argument there for why it is that these theories are consistent or important. So that the truth thing is sort of relevant. Okay, so sort of one problem for these arguments for the consistency of large cardinals is the Kunen inconsistency, or it's at least troubling that large cardinal axioms have been proposed that later turned out to be inconsistent. And the inconsistency isn't just some trivial manipulation. There's subtle reasons that the large cardinals are inconsistent. So typically large cardinal axioms, I mean, the strong ones, are formulated in terms of elementary embeddings, which are, it's a concept from model theory. It's a truth preserving embedding. And you look at elementary embeddings from the whole universe of sets, V, which is just, all the mathematical objects there are, into some submodel of the universe of sets. So some of the mathematical objects, I guess. And as you increase the closure properties of M, you get stronger and stronger principles. Okay, so the ultimate embedding axiom is the existence of an elementary embedding from V to V. Sort of, I mean, it's the ultimate axiom that asserts the existence of one embedding. And Kunen proved that there is no elementary embedding from V to V. So the principle looks like it has a form that's similar to many other large cardinal axioms, but it's just false. So it's hard to say that there's just syntactic reasons for large cardinal axioms to be consistent in that case, because the syntax ultimately leads to an inconsistent principle. Okay, so in fact, it's sort of misleading to say that it's this ultimate axiom that's inconsistent, because really there's a hierarchy of axioms that just eventually reaches inconsistency. It's a little bit more technical to explain. So if you have an elementary embedding, what's the large cardinal that comes from it? So one of them is the critical point of the embedding, which is the least cardinal that is moved by the embedding. So the least cardinal kappa, such that J of kappa is not kappa. And it turns out that if J is not the identity from V to V, then there is a critical point for J. Okay, and then the critical sequence is defined by iterating J starting at its critical point. So you set kappa 0 to be crit j, and then for all n, you set kappa n plus 1 to be j of kappa n of j. So you sort of have the critical point, and then you have j of the critical point, and then you have j of the critical point, and j of the critical point. And, this goes up through all the natural numbers, and then finally kappa omega of j is the supremum of the critical sequence. Okay, so a cardinal is n huge if there's an elementary embedding j from v to m, such that m is closed under kappa n of j sequences. Okay, so a j from v to m that's closed under crit j sequences is a 0 huge cardinal. It's just the same thing as a measurable cardinal, which is one of the most basic large cardinal axioms. And then one huge cardinal is usually called a huge cardinal. And these sort of, I don't know, they came up for the first time in the 60s. I think that they predated the proof of the Kunen inconsistency. But Kunen did introduce huge cardinals. And then, the n huge cardinals are sort of a natural generalization, but okay, so kappa omega is the least fixed point of j above the critical point, and Kunen's proof really shows there are no omega huge cardinals. So if you have any of these elementary embeddings, there's always some finite natural number where the model M isn't closed under kappa n of j sequences. So it's sort of a limitation on the sorts of large cardinals you can express using elementary embeddings. And that, I mean, it's troubling for another reason, because you'd hope that, like the cardinal numbers, the large cardinals go on forever. There are always more and more large cardinal axioms. There shouldn't be a largest axiom of infinity, because you sort of expect large cardinal axioms to reflect the structure of large cardinals themselves. And I don't know, it's very weird to have that sort of bound on these things. It makes them seem like maybe they're not expressing what we think they are. And anyway, the bound is also very weird, because usually, lower down the large cardinal hierarchy, you define principles, and they get stronger and stronger, and you can always define one beyond them. And it's weird to have like this omega sequence of principles, but you can't go beyond them in a certain next one. And it's, I mean, the other weird thing is just the proof is very weird, because it relies very heavily on the axiom of choice, which itself was, at least at one time, a controversial principle. And so it's unknown whether you can prove the theorem without using the axiom of choice. And the question has been open ever since Kunen proved the theorem. It's in the original paper where Kunen proves the Kunen inconsistency. And what happens is, if you drop the axiom of choice and just work in ZF set theory, there's, the large cardinal hierarchy doesn't end. You can, drop choice and see beyond the Kunen inconsistency. And there's a whole large cardinal hierarchy beyond the Kunen inconsistency that, the principles in the hierarchy get extremely strong, and they're beyond really what's understood. And I don't know, it's almost hard to believe that all these principles are consistent, even in the choiceless context. And I mean, it's especially bad if you think that the justification for the consistency of large cardinals is that they're true. Then, either you have to reject the axiom of choice, or you have to explain how the choiceless cardinals are consistent in some other way. Okay, so I wanted to give some examples of choiceless large cardinals. So yeah, the V hierarchy is, just formed by iterating the power set operation, starting with nothing, taking unions. So, you start with the empty set and you take the power set of the empty set and the power set of the power set of the empty set and the union of all those power sets, and then you keep going. Okay. So the weakest choiceless large cardinal axiom, which is actually a little bit below omega huge, maybe, is, there's an elementary embedding from V alpha plus 2 to V alpha plus 2 for some alpha. It's probably consistent with ZFC that there's an elementary embedding from V alpha plus 1 to V alpha plus 1 for some ordinal alpha. But at V alpha plus 2, the Kunen inconsistency theorem kicks in. Okay, so some other principles. This one is sort of non-standard. So the cardinal lambda is definably Berkeley if for any eta below lambda and any alpha above lambda, you can find an embedding from V alpha to V alpha with critical point between eta and lambda. So you can get the critical point arbitrarily high below lambda and get an embedding from any level of the cumulative hierarchy to itself. Sort of interesting thing about this principle. So if you have one of these embeddings that Reinhardt was interested in, then its first fixed point above its critical point, this kappa omega of J cardinal, is always definably Berkeley. But the principle of being definably Berkeley is first order. So sort of it's a nicer principle, and also it's not clear that there is any first order consequence of a J from V to V that is not a consequence of the existence of a definable Berkeley cardinal. And I mean, I don't mean this in a vague sense. I mean, it could literally be true that these two principles have the same first order consequences.
Hey,
which
I have a question. Can you say a little bit about this definably adjective? So in what sense are you talking about? Why is it definably Berkeley?
Oh, okay. So I'll show you. So a cardinal is Berkeley if for any, I don't know if definably Berkeley is a good term. It could go away someday. But a cardinal's Berkeley if for any eta below lambda below alpha, and any subset of V alpha, you can always find a J from V alpha A to V alpha A with the critical point above eta and below lambda. So definably Berkeley, you could also say it's true if you can do this for all ordinal definable A. Or another way to say the last one is for any structure that contains lambda, there's such an elementary embedding. And then for the third one, you could say for any ordinal definable structure that contains lambda, there's an elementary embedding like that. Or actually, sort of, you could say for any definable structure, you can quantify over definable things just using ordinal definability. So that's why it's called that. But anyway, sort of, deflates the problems with the first order definability of Reinhardt cardinals or embeddings from V to V. And I think it's actually a very interesting question whether the two, whether a J from V to V is conservative over a definably Berkeley cardinal. I think that has a good chance of being true. Okay. So mostly all the things I'm going to talk about are going to be consequences of things like a J from V alpha plus 2 to V alpha plus 2, or a definably Berkeley cardinal. And I'm not going to talk at all about Berkeley cardinals, which seem really strong. And those are the ones I think, probably inconsistent, but definably Berkeley is probably okay. So I sort of avoid Berkeley cardinals for that reason. Okay, so the one thing I'm going to say about Berkeley cardinals is I'll show you the proof that there are no Berkeley cardinals if you assume the axiom of choice. And this proof is due to Wooden. The interesting thing about the proof is that, while the Kunen inconsistency theorem, every proof of it seems to involve some sort of combinatorics using AC. The proof of no Berkeley cardinals is just completely direct. So Berkeley cardinals are much stronger than the principle that Kunen refuted, and for that reason they're easier to refute, I guess. So the proof goes this: suppose lambda is the least Berkeley cardinal. So because lambda is the least Berkeley cardinal, there has to be, for any alpha below lambda, there's some witness that alpha is not a Berkeley cardinal. So there's some ordinal beta alpha above lambda or above alpha, and a set A alpha contained in V beta alpha, so that there's no J from V beta alpha A alpha to V beta A alpha with critical point less than or equal to alpha. Okay, so this is just because lambda is the least Berkeley cardinal. Otherwise, there would be a Berkeley cardinal below lambda. Okay, so then you take the supremum of all the betas and you join together all the A alphas, and you take an embedding from the structure V beta and all the A alphas and all their corresponding beta alphas to itself with critical point below lambda. And there has to be such an embedding because lambda is a Berkeley cardinal. Okay, so by the way, the place where you use the axiom of choice is just in the second bullet, right, where you choose the A alphas. Okay, so the thing about this embedding is that it has to move every ordinal, above the critical point of J and below lambda. It should say for every alpha between the critical point of J and lambda. J of alpha can't be alpha because otherwise you could just restrict J to V beta alpha, and that would give you an embedding from V beta alpha A alpha to V beta alpha A alpha with critical point less than or equal to alpha, right? And there is no such embedding by the second bullet point. Okay, so the point here is if J fixes alpha, then it's fixing the A alpha in the structure above, so you can restrict the embedding down and contradict the second bullet point. Okay, so that means that J has no fixed points between its critical point and lambda, and it follows that lambda is the less than or equal to the kappa omega of J. Remember, kappa omega of J is the first fixed point of J greater than or equal to its critical point. Sort of cheating here because I didn't define kappa omega of J in the context of embeddings that don't act on all of V, but it's the same definition. So it just means you take the critical point of J and you apply J repeatedly to it until you finally get to the omega one, and that's a fixed point of J. Okay, so because lambda is less than or equal to the kappa omega of J, you can look at sequence cofinal in the beta n's, in the beta alphas. So it's sort of an abusive notation, but let beta n be equal to beta kappa n of J, whenever that's defined, and let an be equal to a kappa n of J, I guess if that's defined, and fix an embedding K from V beta n an to V beta n an with the critical point of K less than lambda. And then, for each n, k is going to restrict to an elementary embedding from v beta n an to v beta n an. It follows that the critical point of k is strictly above kappa n of j for all n. Okay, and that means that the critical point of k is greater than or equal to lambda. That's a contradiction. Okay, so that's the refutation of Berkeley cardinal. So there's no there's no tricks like in the proof of the Kunen inconsistency. There's this weird case split, but okay. So yeah, we're gonna work below Berkeley cardinals. Another thing this shows is that the first definably Berkeley cardinal is smaller than the first Berkeley cardinal, if you're not assuming AC. Okay, so yeah, are the choiceless large cardinal axioms consistent? There's not a lot of evidence for it. There's no, it's not clear that there's a conception of the universe of sets in which all the choiceless cardinals are true. I mean, the weird thing is that if you drop the axiom of choice, it's so hard to prove anything that it's never really clear what it is you're talking about. I mean, there are just so many things that are independent in ZF alone. So you're trying to work with these large cardinal axioms, and they do some stuff for you, but there's so much else that you just can't answer. So it's not obvious what principles you should be assuming in addition to the choiceless large cardinal axioms to get a good theory. So it makes it harder to conceive of some, universe in which the axioms are true. Okay, it's also apparently, and this is a related fact, it seems impossible to develop inner model theory for choiceless cardinals. So, the inner models are our technique for getting structures in which we know all the basic principles, and we have large cardinal axioms, and those, it's not just that it seems like it would be hard to build the inner models for them. There are theoretical reasons for believing that, in fact, if the choiceless large cardinals are consistent at all, then inner model theory can't reach even smaller large cardinals like supercompact cardinals that are consistent with the axiom of choice. So there's reason to believe that, if you think that inner model theory will reach supercompact cardinals, then you should probably think that Berkeley cardinals are inconsistent. But it could be that, some part of the choiceless hierarchy is consistent, and then beyond it, there's an inconsistency. Okay, so until recently, also there was not much interesting structure theory. So there's one paper that's published, which is the Bulgaria Kolner wooden paper on choiceless large cardinals. And that's sort of establishing sort of basic large cardinal things, like which large cardinal is below another one. But even though I don't know what structure theory means, I don't know if that is exactly structure theory. So there's some, I mean, the rest of the results I'm going to talk about are sort of the structure theory of choiceless cardinals. And I don't know, it's interesting because the choiceless cardinals seem to imply they have many more consequences than the usual large cardinals in some way. And I don't know if that makes it look like they're consistent or inconsistent, actually. But it seems like it should be possible to figure out which one it is, at least. Okay, so the first thing I want to talk about is periodicity. So the periodicity is just periodicity of order 2. So there are differences in basically the structure of the levels. The epsilon, where epsilon is an even ordinal, which just means epsilons of the form lambda plus 2n for some limit ordinal lambda and natural number n. and the structure of the odd levels, the epsilon plus 1. Okay, but on the other hand, the even levels look a lot like each other and the odd levels look a lot like each other. And that sort of thing doesn't usually happen in set theory. Normally you have something like the limit levels all look alike, and then the successor levels, you can't say that much about them. But here, there's this periodicity. So the most basic differences just involve the structure of elementary embeddings, but sort of deeper differences just involve, purely structural dissimilarities. So, structural properties that don't have to do with large cardinals, but follow from the large cardinals, sort of more interesting. Okay, so yeah, there's no periodicity theorems in large cardinal theory, basically. The only other place in set theory where there are periodicity theorems is determinacy. So in determinacy, there are these things called the periodicity theorems, and they're sort of periodicity theorems about alternating quantifiers. So there's a difference between the pi 1 2n sets and the pi 1 2n plus 1 sets. And I guess something that was pointed out to me by Farmer Schlutzenberg is that the periodicity there is sort of built into the definitions, because their quantifiers are alternating at a time, but here there's nothing really built into the definition of the V alphas that would make you suspect that there should be a difference between the even and odd levels. Okay, so yeah, so the basic difference has to do with definability of embeddings. So I was already talking about how Reinhardt embedding J from V to V can't be definable over V. So that's attributed to Suzuki, although may have been known to Kunen. So you can't have a definable embedding from V to V. And whenever I say definable, I mean definable from parameters. Okay, so that makes the Kunen inconsistency as stated about Reinhardt embeddings sort of a weird thing, because normally in set theory, when you talk about the existence of some class, you're talking about definable classes. But here, to really assert the Kunen inconsistency theorem, you really want to be talking about arbitrary classes, which has its own philosophical problems. They're sort of unrelated because, anyway. So, but there's actually what I think is a more interesting instance of the undefinability results. Just refers to sets. So this was Schlutzenberg's idea. So he proved that if you have any limit ordinal lambda, there's no definable embedding from V lambda to V lambda. And it's sort of a localization of the Suzuki proof. And then it's a folklore fact that, given a limit ordinal lambda, any elementary embedding from V lambda plus 1 to V lambda plus 1 is definable over V lambda plus 1, just using the restriction of the embedding to V lambda. So the way you do it is, if you have a set in V lambda plus 1, which is just a subset of V lambda, then to move it using J, you just take the union of what the embedding does to all the pieces of the set A. Okay, so and that's all encoded by J restriction V lambda, and J restriction V lambda is a parameter in V lambda plus 1. So there's this difference, which is not surprising, between the limit levels and the successor of limit levels. There are no definable embeddings of the limit levels, and there are no undefinable embeddings of the successor of limit levels. Okay, and Schlotzenberg then asked what happens at v lambda plus 2 and v lambda plus 3. Okay, so I proved that if you have an even ordinal, then there's no elementary embedding definable over v epsilon from v epsilon to itself. And on the other hand, for every odd ordinal, the embeddings from that level to itself are definable over the level. And Schlotzenberg also proved this independently, which is why you should always publish as soon as possible. Okay, so the theta sequence. So this sort of definability periodicity leads to purely structural periodicity in terms of the sequence of cardinals theta alpha. So here theta alpha is the supremum of all ordinals eta that are the surjective image of v sub xi for some xi less than alpha. Okay, so I'm going to give more examples than necessary. So theta omega is just omega, right? The supremum of all ordinals that are the image of some finite Vn. Theta omega plus 1 is omega 1. The surjective image of v omega is always a countable ordinal. Okay, assuming AC, theta omega plus 2 is the continuum plus, and more generally, theta omega plus alpha is always the supremum of the strict supremum of the Beth sub x's for xi less than alpha. So that sort of tells you under ZFC what these cardinals are vaguely, because you can't compute really what the Beth sequence is. And then in a sort of more similar context to the one we're in, under the axiom of determinacy, theta omega plus 2, which is sort of the key cardinal under AD, or one of them, depending on what part of AD you're studying. Theta is a strong limit cardinal, which means so that you have to define strong limit cardinal differently in the context of ZF and the context of ZFC. So what I mean by strong limit cardinal is that whenever you have an ordinal beta less than theta omega plus 2, there's never a surjection from its power set onto theta omega plus 2. And okay, so that's pretty different from being the continuum plus, right? If theta omega plus 2 is the continuum plus, then obviously the power of the continuum surjects onto theta omega plus 2. And then under AD, and maybe you need DC here, theta omega plus 3 is the successor of theta. And the value of theta omega plus 4 can't be determined from AD. Okay, so there's a sort of interesting pattern. So theta omega is omega, theta omega plus 1 is the successor of omega. So omega is a strong limit cardinal, and then theta omega plus 2 is again a strong limit cardinal, and theta omega plus 3 is its successor. Okay, so there's a pattern for 4 cardinals, and maybe try to generalize that. So the conjecture is under rank-to-rank cardinals, there's a generalization of this. So if epsilon's an even ordinal, and there's a j from v epsilon plus 2 to v epsilon plus 2, then theta epsilon is a strong limit cardinal, and theta epsilon plus 1 is its successor. This, I mean, it would be nice, it would definitely establish a very strong structural form of periodicity for large enough ordinals, assuming choiceless large cardinal principles. But I don't know how to prove it, so it's some work to be done. So for epsilon a limit ordinal, this is trivial. So just in CF, you can prove that theta epsilon is always a strong limit cardinal, and theta epsilon plus 1 is always the successor of theta epsilon. So the question is whether this generalizes, or whether you can use choiceless large cardinals to generalize this. And if that's true, it's also saying that the choiceless large cardinals say a lot more about this, well, basically the Beth sequence or the theta sequence than the cardinals consistent with ZFC do, because, you know, there's the sort of Easton phenomenon that the ZFC large cardinals don't decide a whole lot about the Beth alphas for successor ordinals alpha. So the conjecture is sort of you know, some sort of solution to the continuum, the generalized continuum problem for large enough ordinals from, you know, false large cardinal axioms, but hopefully consistent ones. Okay, so there's I think there's a lot of evidence that the conjecture is true, although I do worry that it's independent, because I don't know, it's hard to prove. Okay, so the theorem, which is sort of partial, is that if epsilon's an even ordinal, and you have a j from v epsilon plus 2 to v epsilon plus 2, then I don't know how to prove that theta epsilon plus 2 is a strong limit cardinal, but I can handle all the ordinals less than theta epsilon plus 1 to the iterated successor kappa omega of j many times. So that's so, you know, for any of those ordinals, there's no surjection from p of eta up to theta epsilon plus 2. You just have to, you know, to prove the conjecture, you just have to get that all the way up to theta epsilon plus 2, which is a long way away from theta epsilon plus 1 plus kappa omega of j. Okay, so for example, I mean, the most basic non-trivial thing the theorem is saying is that there's no surjection from the power set of theta epsilon plus 1 plus to theta epsilon plus 2, which is not obvious. I mean, it's not even obvious that theta epsilon plus 2 is not equal to theta epsilon plus 1 plus. So the theorem is substantial, at least, but it doesn't say that theta epsilon plus 2 is a strong limit. So the way you get it is you sort of use that if there was such a surjection, you could contradict the definability, the undefinability of embeddings at the even level. So the sort of you need to strengthen it. Remember that the theorem that Farmer and I proved was that if there are no definable embeddings from v epsilon to v epsilon where epsilon is even, and you need to strengthen that to look instead of at the embeddings on v epsilon, just to look at the embeddings restricted to ordinals. And so that's what this theorem is doing. So it says if you have a j, I stated it in a weak form, but if you have a j from v to v and an epsilon that's even above the critical point and fixed by j, then j on theta epsilon is an OD from any parameter in v epsilon. So, I mean, that's a pretty strong undefinability result, right? You can't, like, for example, if you have j from v to v and you're looking at kappa omega of j, that the restriction of j to that is not OD from any parameters in v kappa omega of j. That's wasn't known. I answered some questions. question from Lutzenberg's paper too. Okay. So for the odd thetas, remember the conjecture was that theta epsilon plus 1 is the successor of theta epsilon. And I don't know how to prove that either, but you can show that the odd thetas are very small, sort of. So if you have an even ordinal epsilon and an elementary embedding from v epsilon plus 3 to itself, then in between theta epsilon plus 2 and theta epsilon plus 3, there are fewer than kappa, critical point of J, many regular cardinals. And the annoying thing is that you would like to say, well, therefore, theta epsilon plus 3 is strictly below theta epsilon plus 2 to the, plus crit J. And that, I mean, you can't, because in ZFC, that would be enough because you would know that every successor cardinal is regular. So there are kappa, there are crit J many regular cardinals between theta epsilon plus 2 and theta epsilon plus 2 plus crit J. But you can't prove that in ZF. So that's a problem. And actually, it seems like the choiceless cardinals should imply that there are successor cardinals that are singular. But I don't, there's an open question there, very open. So if you have a definably Berkeley cardinal, does there have to be a singular successor cardinal above lambda? And is it consistent that every single cardinal above lambda is singular? So that sort of version of the, the Giddick independence result for Berkeley cardinals, or definably Berkeley cardinals. Okay, so if you give yourself some choice, you can do a little better. Okay, so lambda DC, lambda dependent choices it can be stated as a local version of Zorn's principle, or Zorn's lemma. Okay, lambda DC is that if you have a partial order in which every chain of size less than lambda has an upper bound, then either the partial order contains a maximal element or it contains a chain of order type lambda. And then I need another choice principle. So it's just a local version of the axiom of collection. So if X and Y are sets, then X-Y collection asserts that if you have a relation on X times Y, then there's a subrelation of R that has the same domain as R, and its range is the surjective image of X, or equivalently, the whole relation is the surjective image of X. Okay, so the point of this is if you had a choice function for R, then of course the choice function is the surjective image of its domain. So XY collection is in one sense a local version of the axiom of collection, and in another sense it's a fuzzy version of the axiom of choice. Okay, now say you have a definably Berkeley cardinal lambda, and you have lambda DC, and you take some even ordinal epsilon above lambda, and you have v epsilon plus 1, v epsilon plus 2 collection. V epsilon plus 1, v epsilon plus 2 collection in this context you can think of as being a strong way of saying that theta epsilon plus 2 is regular. You have to sort of think that through. In the context of AD, for example, v omega plus 1, v omega plus 2 collection is equivalent to the statement that theta is regular. So from these principles, you can prove theta epsilon plus 2 is a strong limit cardinal. And in fact, for any eta below theta epsilon plus 2, there's a surjection from v epsilon plus 1 to the power set of eta. And theta epsilon plus 2 is a limit of regular cardinals. So, and of course, theta epsilon plus 2 is regular. So there's a lot more you can say from these weak choice principles, and it just shows it's not clear what the choice principles you should be assuming are in the context of choiceless cardinals, because you should never be working in just ZF alone. It's a cruel theory. Let's see. And also, I mean, this theorem shows that there's a big difference between the odds and the evens if you give yourself these principles, right? Because theta epsilon plus 1 couldn't even have crit j many regular cardinals between it and the cardinal below, but theta epsilon plus 2 is a limit of regular cardinals, which means there are theta epsilon plus 2 many regular cardinals between theta epsilon plus 2 and theta epsilon plus 1. Okay, so now I want to talk about ultrafilters. I'll sort of rush through, I guess. So Joel, when should I stop? Because there's supposed to be time for questions, but I think there won't be that many questions.
I think there will be questions. So it would be good if you could allow some time for questions. I mean, we have 90 minutes altogether, including questions.
So maybe I'll take 10 more minutes or something?
Yeah, that would be fine, I think. Yeah.
Okay, great. Okay, so under AD, the structure of ultrafilters on ordinals is very important. I mean, it's used to determine a lot of the other structure of sets of ordinals and of the projective ordinals. It's a basic part of the set theory of the axiom of determinacy. And it turns out that the structure of ultrafilters on ordinals in the context of choiceless cardinals is also pretty interesting and complex and analogous to the AD structure of ultrafilters. So the first analogy that was noticed is this theorem Solove, which says that under AD, omega 1 is a measurable cardinal, and actually the club filter on omega 1 is a countably complete ultrafilter. So it's measurable in the combinatorial sense. And wouldn't generalize this. If you have a j from v lambda plus 2 to v lambda plus 2, and you have lambda dc, then lambda plus is a measurable cardinal. And in fact, the omega club filter restricted to a stationary set is a lambda plus complete ultrafilter. So it's a weird analogy, sort of that both the axiom of determinacy and choiceless large cardinal axioms are ruling out the existence of pathological undefinable sets. The pathological sets are stationary, co-stationary sets, which can never really be definable. The weird thing is that the choiceless large cardinals do this by asserting the existence of other sort of pathological undefinable sets, namely the embeddings from v lambda plus 2 to v lambda plus 2. Although that pathological is maybe a stretch, but definitely undefinable. Okay. So I want to talk about further ultrafilter structure in this context and more analogies to AD. So Wage's lemma is an important theorem under AD. Okay, if delta is an ordinal, a Lipschitz function from the power set of delta to the power set of delta is a function which, if you take a subset of delta to compute what h of the set is up to alpha, you only need to know the set up to alpha. Okay, so for any a contained in delta and any alpha less than or equal to delta, h of a up to alpha is the same thing as h of a cut to alpha. Okay. in the context of when delta is omega, this is the same thing as a Lipschitz function on the power set of omega, really a Lipschitz function on the Cantor space to the omega. So if you have two sets that agree up to alpha, then the image of the sets agree up to alpha again. Okay, and the Lipschitz order on subsets of P of delta, this is just some generalized descriptive set theory thing. X is below Y in the Lipschitz order if there's a Lipschitz reduction from X to Y. So there's an H from P of delta to P of delta, so that if a point X belongs to capital X, if and only if H of X belongs to capital Y. Okay. Wage's lemma is the statement that the Lipschitz order is almost linear on subsets of the power of omega under AD. So that's just, if you have two sets X and Y, either X Lipschitz reduces to Y or Y Lipschitz reduces to the complement of X. And this is really useful, especially because under AD plus DC, the Lipschitz order is well-founded. That's the Martin-Monk theorem. So you basically have a pre-well order of all the subsets of the power of omega. So it's a complexity order on subsets of the power of omega that, compares the complexity of every pair of subsets. The Ketenin order is the analogous thing for ultrafilters. So it's the Lipschitz order in the category of countably complete Boolean algebras. I just mean it's the order on ultrafilters by Lipschitz reductions that are also countably complete homomorphisms. So one ultrafilter is Ketenin below another. If there's a Lipschitz countably complete homomorphism from P of delta to P of delta that has A is in U if and only if H of A is in W. Okay. So, sorry, in ZF plus DC, one can prove that the Ketenin order is a well-founded partial order on ultrafilters. You can't prove that about the Lipschitz order, I don't think, in ZF plus DC. In the context of ZFC, the ultra power axiom, which is what I wrote my thesis about, is just saying that the Ketenin order is linear. And from that, you can prove all kinds of stuff about ultrafilters and large cardinals. I mean, the thing about it is large cardinals and the theory of countably complete ultrafilters are very closely related. Anyway, so it's useful to have this principle for countably complete ultrafilters. That the ultra power axiom basically answers all the basic structural questions about countably complete ultrafilters. But the only way of getting models of UA is to build inner models of large cardinals. So it's open whether UA is consistent with the large cardinals beyond today's inner model theory. But under choiceless large cardinal axioms, you can almost just prove UA. So that gives you a lot of structure for the ultrafilters in this context. So say you have a definably Berkeley cardinal and you have lambda DC. By the way, that means that lambda is the least definably Berkeley cardinal. Okay, then if you have any ordinal delta and you look at the ultrafilters on delta of rank alpha in the Ketenin order, then that set has cardinality strictly below lambda. So that means the Ketenin order is almost linear. Every level has size less than lambda. And also, if you take any set of incomparable ultrafilters, it has cardinality bounded by lambda. So it's almost like the Ketenin order is some sort of generalization of a well quasi-order. But it's almost linear, just like the wage order is almost linear, except here the bound is lambda instead of 2. Or 3 on the anti-chains. Okay, the idea is the reductions in the Ketenin order that you get in this context are actually elementary embeddings. So if you have a j from v alpha to v alpha, then if you restrict it to the power of delta, where delta is a fixed point of j, you get a countably complete Lipschitz homomorphism. And in fact, you don't have to look at the Ketenin order. You could look at the order under embeddings like this, and that would have the same result true if it, even that order is almost linear. Okay, one more result like this. You can use the Ketenin order again to prove that every lambda plus complete filter on an ordinal extends to a lambda plus complete ultrafilter. I'm not going to go through the proof, but basically you look at the Ketenin minimal filter that's a counterexample. That's just the same order, but on filters instead. And then you sort of find a filter that's compatible with it that you know extends to an ultrafilter. Okay. You can prove some ordinal definability properties of ultrafilters. I'm just going to skip them. Okay, so the last thing I want to talk about is are the choiceless large cardinals consistent? So there are a bunch of large cardinal axioms approaching the choiceless large cardinal axioms that are thought to be consistent in CFC. The one I'm interested in here is I0, which says that there's a j from v lambda plus 1 to v lambda plus 1 with critical point below lambda. That's due to Wooden. His first proof of ADL of R used the principle I0, which is much stronger than the principle you actually need. Okay. Lutzenberg recently showed that ZFC plus I0 is equiconsistent with the existence of a j from v lambda plus 2 to v lambda plus 2 and lambda dc, which is also equiconsistent with an omega huge cardinal with enough dc. Okay. So the simplest large cardinal axiom beyond choice is actually consistent relative to traditional large cardinal axioms. So large cardinal axioms consistent with choice, or at least believed to be consistent with choice. So I think this is very strong evidence that all these principles are consistent, these three principles, I0 and v lambda plus 2 to v lambda plus 2 and omega huge. So could there be something like that beyond I0? This is the last slide. So first of all, you have to go beyond I0 to get a j from v lambda plus 3 to v lambda plus 3, right? Because j from v lambda plus 3 to v lambda plus 3 plus aleph 0 dc, which is just usual dc, implies that ZFC plus I0 is consistent. So ZFC plus I0 can't be equiconsistent with j from v lambda plus 3 to v lambda plus 3. And it's actually an annoying question whether you can get rid of the DC assumption. So there's a hierarchy of inner models beyond L of v lambda plus 1, and corresponding to them, there are large cardinal axioms beyond I0. Just, there's a j from the model to itself with critical point below lambda. And these are sort of analogous to the hierarchy of models of determinacy beyond L of R and the corresponding determinacy hypotheses for these models. So like L of R sharp and the minimal model of ADR. It's plausible that all the choiceless large cardinals that are consistent line up with levels of Wooden's hierarchy beyond L of v lambda plus 1. And there's some evidence that, for example, a j from v lambda plus 3 to v lambda plus 3 is equiconsistent with Wooden's analog of ADR at the level of, I0 cardinals. So if this is true, there's a path up proving the consistency of choiceless large cardinal axioms from the axioms in Wooden's hierarchy, which would sort of bolster our belief in the consistency of the principles in both hierarchies. And I think that's the best hope that we have of figuring out which of the choiceless large cardinal axioms are consistent. And I mean, there's even still a chance that that this hierarchy reaches up just high enough to prove Reinhardt cardinals are consistent, yet doesn't go high enough to ruin the chances that intermodal theory extends to supercompact cardinals. So it's a possibility that neither of the talks I've given in the last 2 weeks are vacuous. Okay, thanks.
Well, thank you very much, Gabe. That was great. So let's all give him a hand. And for handling questions, if you have a question, just write the word question in the chat, and then I'll call on people. You don't have to type your question. You can just, if I know who to call on, then you can unmute yourself. Let's see. So why don't, while we're waiting for that, let me ask my question. I'm going to change the view here to gallery. Okay. Right. So I remember speaking with Solovey once after he, so he had proved, of course, this great theorem about the consistency of all sets of reals being Lebesgue measurable and so on without AC. And he indicated to me that that his initial expectation after proving that theorem was that the analysts would all adopt this great theory and have all sets of reals being Lebesgue measurable and so on. And he was disappointed that they didn't. And what's the lesson to learn from that? And maybe the lesson is that, look, the intuition of mathematicians for the axiom of choice is incredibly strong, and they will never give it up. And maybe we shouldn't either. And so how should we think about these large cardinals up there that we have to deny choice to adopt? And why shouldn't we just take the Kunen inconsistency as the end of the matter? In other words, what is the benefit of looking at those large cardinal notions given that they're contradicting AC?
Well, I think maybe the last thing I said is an answer to that. There, hopefully the large cardinals at the level of AC and the large cardinals beyond choice are actually part of one hierarchy, and the large cardinals beyond choice are actually more than an analog of AD, so that they hold in certain restricted submodels of the universe of sets. So even though the axiom of determinacy isn't true in V with AC, there are still good reasons to study inner models of the axiom of determinacy. And I think that's probably what's the same thing that's going on with the choiceless cardinals. Now, if it isn't though, and the choiceless cardinals go up beyond anything that can be interpreted in ZFC, then I think they're still worth studying. And even if mathematicians aren't going to adopt them, there's still a valid question of whether they are true or whether they form a theory that it should be accepted beyond AC. Just because if AC sort of limits the power of theories to interpret other theories, then it's not clear that, just independent of pragmatic issues like whether any mathematician will ever even hear of what a Reinhardt cardinal is, I think there's still a question of which of those should actually be adopted.
Okay, well, thank you very much. And Philip Welch has a question.
All right. Hi, Gabe. Yeah, thanks very much for your talk, by the way. I mean, that was really interesting. I just had a technical question about UA, ultra power axiom. You put up a question there about it being consistent in ZFC with supercompacts. Is that because, I mean, why did you say supercompact? Is that because you think that they are consistent? We are close to showing it's consistent with supercompacts, or What do we know about the ZFC consistency of UA?
So UA is known to be consistent with, a wooden limit of wooden cardinals. So up until the inner model hierarchy is no longer known unconditionally to exist. So given the iterability hypotheses, consistent with a super strong cardinal, and actually with a kappa plus n super compact cardinal for any n. So UA is consistent with Itai Neiman pointed out to me that means that UA plus ZFC minus replacement plus the super compact cardinal is consistent. But yeah, so the final frontier of inner model theory is super compact cardinals. And the hope is that if you can build an inner model with a super compact cardinal, then you get inner models with all.
So the consistency of UA is kind of bound up with showing that via inner model theory.
Right, yeah. It's sort of like consistency of UA with a super compact cardinal is a test question for inner model theory at the level of the super compact cardinal. But also most of the interesting consequences of UA are at the level of a super compact cardinal. So I think that UA is consistent with a super compact cardinal. It seems, again, it would be cruel if it weren't.
Okay, thanks very much.
Let's see, Dan Isaacson has a question. So if he's unmuting.
Right, okay, sorry, thanks very much. My question is probably superseded by the question, Joel, that you asked, but in my own very ignorant way, I wanted to ask something about why one should be interested at all in a version, well, in versions of set theory in which one contradicts the axiom of choice, since the axiom of choice is true, if I may put it that way. I take, so for example, axiom of determinacy contradicts choice, but I take it in the clash between them, choice wins in the sense that the only degrees, the only levels of axiom of determinacy that are thought to be mathematically or even set theoretically important are those that don't contradict choice. So I'm just wondering what the motivation can be for the enterprise.
Right. So before the axiom of determinacy was proved consistent, in inner models, it was studied and usually is studied still just in the context of ZF plus AD. And similarly, in this context, we're studying ZF plus these choiceless large cardinal axioms, hoping to find the right model of the choiceless large cardinal axioms. We don't know yet exactly what the form of that model is, but probably it's a submodel in the universe of sets that satisfies these axioms. Now, another question, though, is whether the truth of the axiom of choice is really as well established as your question suggests that it is. The axiom of choice is a great axiom, but how strong really are the philosophical arguments for the axiom of choice? I've never been convinced of the axiom of choice by maximality. Mostly the axiom of choice convinces you by convenience, in my opinion.
Well, one argument would be that there's that in the finite case, it's logically valid.
And so is the axiom of determinacy.
Ah, okay. Yes, all right. That's an answer there. Right. Anyway, so, but maybe ask this question. I mean, is the idea at the end of this investigation, let's suppose that the study of choiceless cardinals that you're working out establishes this hierarchy, is that going to be a hierarchy within V, or is it going to be another hierarchy?
I think hopefully another hierarchy, right? Because you'd hope that the cardinals are somehow compatible with the axiom of choice and that everything can be put together into one picture. So that the hope is that the hierarchy lines up with another hierarchy of large cardinals that are true in V, where, you know, V is the universe that we currently conceive to satisfy the axiom of choice. And that seems like the most probable way that the consistency of these principles will be established.
Right.
But there are, you know, other darker futures where everything bifurcates.
Right.
Maybe more exciting.
Thank you. Exciting.
Okay, let's see. Aaron has a question. Oh, were you done, Dan? Or
Yes, no, I'm done.
okay, Aaron
Thanks.
Conley has a question.
Oh, thank you. That was a very interesting talk. And I have sort of it's like a lighthearted comment, kind of serious, but it's related to the previous some of the previous questions. And like to me, when I think of a large cardinal, the number one defining feature is that it's a model of ZFC. It's somewhere where you can do mathematics. So, but maybe that's not like so common. I don't know. But I thought that your periodicity phenomenon was really interesting, and it reminded me of how e to the x is not periodic when the domain is the real numbers, but it is periodic when the domain is the complex numbers. So maybe these are imaginary large cardinals or complex large cardinals, something like that.
That's funny. That's interesting.
Changing the landscape, but very interesting.
So that's great, Aaron. I have another question, and that is, okay, in ZFC large cardinal set theory, some of the large cardinal notions are defined using the V alpha hierarchy. For example, it's common to define theta strong to mean that V theta is contained in M. But sometimes people criticize this and they say, look, we shouldn't be using V theta because that's the wrong structure. It doesn't have right closure properties and so on. We should be using H kappa or H theta, something like that, the hereditarily sized less than theta sets. And so they want to define a notion of strongness, say, using the H theta hierarchy instead of the V alpha hierarchy. And I think those arguments are quite strong. And so usually when I talk about large cardinals, I define them that way. But in your account, everything's all about the V alpha hierarchy, and also the H kappa hierarchy doesn't really make sense without the axiom of choice, because I guess it's not linearly ordered even. And so what do you have any thoughts on that? I mean, wouldn't the criticisms about the sort of wrong-headedness of the V alpha hierarchy still apply to those choiceless axioms just as much as they do, say, to defining strongness that way?
Well, I guess with strongness, I don't think it's wrong-headed to define it in terms of the V alpha hierarchy. I mean, maybe the indexing is a little bit worse. If you look at my paper, actually, mostly I am working with an analog of the H hierarchy. So each V alpha is I want to be careful, but I think bi-interpretable with a structure of the form H alpha, which is really the union of all transitive sets that are the surjective image of V sub xi for some xi less than alpha.
Are you doing that in the choiceless context?
Yeah, that's fine. It's okay in the choiceless context. And it's actually much easier to work with those structures than the V alphas, because there are all these coding.
Oh, well, that
problems.
supports my point then. So why aren't
Yeah.
notions made?
Those structures are
Why aren't we defining the large cardinal notions in terms of that hierarchy instead? That's my question, really.
well, I mean, that hierarchy is itself defined in terms of the v sub x's, and the two principles are equivalent. J from h lambda, which is what I called it, h sub lambda, probably also bad notation, to h sub lambda. It's the same as j from v lambda to v lambda. So
what does h lambda mean without choice, though? I mean, well, you define it
h sub lambda.
hierarchy.
So I shouldn't have called it h sub lambda, because instead of h round bracket lambda, it's not very good notation. But h sub lambda was just the union of all transitive sets that are the surjective image of v sub xi.
Oh, you use surjection instead of bijection. I see. Okay.
Yeah.
That's great. I like that idea a lot. Yeah, that's really great.
Yeah, but Asaf was telling me about a different version of the h kappas, which also made sense in ZF, and stratified V into an even finer hierarchy. So you can do these things. An annoying problem with them is that you're no longer getting models of replacement or collection even. I mean, or more strongly, you're not getting models of collection. So there are some ways in which it's deceptive to think about, because you're drawn back into the things you know and love from AC, which you can't take for granted.
Right, thank you very much. So Asaf is here. I don't know if he has, oh, Boban has a question. So Boban,
yes, hi, thanks for the very nice talk. We believe, and we have strong evidence, that large cardinal axioms are linearly ordered, at least in the choice context. Do you think that would extend to the choiceless large cardinals, or maybe there are some incomparable choiceless large cardinal axioms?
In terms of consistency strength?
Right.
My guess is that they would still be linearly ordered, except so there are really annoying problems about the ordering of large cardinals at this level, and it could be if actually the large cardinals in the choiceless hierarchy go up so high that they imply the failure of inner model theory. That would kill the actual only technique we have for showing the linearity of the axioms. So there would no longer be good reason to believe that there is a linearity phenomenon. But the consistency strength order asks about provability in weak systems, and it's sort of hard to believe that the question of whether con this theory implies con that theory is going to be undecidable. But who knows?
okay, are there any other questions? I guess not. So let's thank Gabe again. It was a really great talk. So thank you very much.
Thanks for inviting. It was an honor to speak at last.
And let me announce that in 2 weeks, on December 2nd, we're going to have Cameron Williams here speaking about the geology of inner mantles. And so please come back in 2 weeks, and hope to see everybody there. This video is going to be posted on the YouTube channel in the next couple days. So, okay. Thanks very much for coming, and bye.
Bye.
Bye. Thank you so much.